In this video, we're going to take a look at our first really big idea in calculus, maybe the second. Limit might be the first, but our second, the idea that's going to drive us here in calculus. One, that's the idea of the derivative. That derivative is just the slope of that tangent line. Right? So remember, if we have 2 points, we have this curve, and our first point is x, and it has a function value of f of x. And we have our second value as x plus delta x as an x value. And the slope between these 2 points, change in y, is f of x plus delta x minus f of x over x plus delta x minus x. And so the x's would cancel, and we're just left with the change in x on bottom, delta x. But we're going to let that value of delta x right there, that value, we're letting that go to 0 so that the function value is of the second point is approaching the function value of the first point. So we're trying to find out what is the slope exactly at the point. And so we can write this as a function, right? So we're describing this very generally. So that derivative, we can think of that as an instantaneous rate of change. What's the rate of change at a split moment in time? Or we can think of it as slope of a tangent line. When we go through this process, we call it differentiation. If that derivative exists, we say that the function is differentiable. When we look at our derivative, we have lots and lots of different notations. So one of the notations that we have here is f prime of x, right? So that apostrophe, that's our Newton notation for the derivative. We have Leibniz notation, dy dx, the derivative of y with respect to x. We might write df dx, right? So derivative of f with respect to x, or the derivative with respect to x of the function f of x. We might use a capital D as like a differential operator and say we're taking the derivative with respect to x of our function y. All those notations, different notations that we might use depending on setting. All right, so let's look at an example. So here we're going to find the derivative of our function, x squared minus 3x plus 1. We will use that derivative to find the slope of the tangent line at 2, negative 1. So let's find the derivative first. Right? So our definition is the limit as delta x approaches 0, f of x plus delta x minus f of x all over delta x. And so, for this problem, we have our function here. We're going to take x plus delta x. We're going to plug that in place of all the x values. So we have a limit as delta x approaches 0. We have x plus delta x squared, right? So we replace the first x with x plus delta x, minus 3 times x plus delta x plus 1. So that's all f of x plus delta x. And then we're going to subtract f of x. So f of x is x squared minus 3x plus 1. And all of that's divided by delta x. Notice if you plugged in 0 for delta x right now, you're going to get 0 over 0. That suggests that maybe we could get some sort of cancellation that will happen. And so we're going to do some algebra to try to see if we can find out what kind of cancellation happens. Right? So we haven't done direct substitution yet. We're going to need to square and distribute, do some algebra things. We need to distribute this negative to all 3 of those pieces. Right, so we have a limit as delta x approaches 0. When we FOIL out x plus delta x squared, we'll get x squared plus 2x delta x plus delta x squared. And when we distribute the negative 3, we get minus 3x minus 3 delta x. Then we have that plus 1. And then if we distribute the negative, negative minus x squared plus 3x minus 1, all over delta x. Now some really nice things happen on top, right? So that x squared plus 2x, delta x plus the delta x squared, that all comes from foiling out x plus delta x squared. So that's some algebra stuff you might want to take a look at. So cancellation, that x squared term cancels with the x squared term over here. The minus 3x cancels with the positive 3x, and the plus 1 cancels with the minus 1. And so we have left on top 2x delta x plus delta x squared minus 3 delta x. All of that's over delta x. If we did direct substitution right now, we still have 0 over 0. But we notice that everything on top has a delta x involved in it. So we can factor a delta x out of the top. And so if we factor a delta x out of the top, we're left with 2x plus delta x minus 3 all over delta x. So our delta x's there, those are going to cancel. And if we do direct substitution at this point in time, we get 2x plus 0, and so we can skip that, minus 3. That is our derivative. Fantastic. Now, that's only one part of this problem. We're also asked to find the slope of the tangent line, right? So to find the slope of the tangent line, we're also asked to write the equation. But let's find the slope. We went through all this work to find the derivative. So if we're going to find the slope of the tangent line at, let's see, at 2, negative 1, we're just going to plug that x value. We're finding the derivative at our x value of 2. We're plugging 2 in to our derivative. So we have 2 times 2 minus 3. And when we do that, we get a slope of 1. That is the slope of the tangent line. It is the derivative at a point. Fantastic. So now if we want to write the equation of the tangent line, right? So to write our equation for the tangent line, we're looking at the point 2, negative 1 and a slope of 1. We can write that tangent line in point slope form. So we can take y minus the y value of the point, so y minus negative 1, is equal to the slope 1 times x minus the x value of the point, so 2. So that's point slope form. You can go through and do some algebra and solve this for y. If you solve it for y, you will end up with the equation of a line y equals x minus 3. That is the equation of our line. Fantastic. And we could write it in point slope or slope intercept. That form doesn't really matter. All right. In our next video, we will take a look at some more examples. We will see you there.